So now we come to a term that we have been sort of dancing around for quite a large part of this set of lectures so far, which is the FPGA, right? What are FPGAs? Why do they exist? And what can we do with them is something that we are going to briefly touch upon here, but we will be using them extensively throughout the course. So let's try and understand a little bit about the background, where did they come from? The first question to ask is, okay, so FPGAs refer to some kind of programmable hardware. Why do you need programmable hardware in the first case, and what exactly do you mean by programmable hardware in any case, right? So when we say programmable hardware, we are not talking about a microcontroller or a chip where you can write a program and run it on the chip. That's software, right? By programmable hardware we mean something else, and that will hopefully become clear in a moment. Now the problem is, I already mentioned foundries, right? These are the factories where chips are actually made. It turns out that even setting up a foundry is an extremely capital intensive process, right? It is a very expensive process, typically in the tens of billions of dollars range in order to set up a foundry in today's technology, right? Even one of the older technologies would be fairly expensive, right? It's not really going to be cheap. And let's say that you have designed some kind of IP, right? Maybe a processor, maybe some kind of signal processing core or some other particular element that you want actually to get fabricated as a chip. It turns out that there is a huge non-recurring engineering cost associated with each of these chips, meaning that even to get a single chip out of that, you probably have to invest several $100,000 or possibly in the range of $1 million or so, right? Even for a single chip. Now that basically puts it out of range of pretty much all individuals and even many companies, right? Not only that, it also takes a long turnaround time, and during this time you absolutely cannot afford to have any mistakes in your design, because essentially you are going to come back with faulty silicon, and well, you have just sunk all that cost without getting anything back for it. Okay, so this kind of makes it difficult to actually experiment with digital hardware, but we would like to have the ability to do something called rapid prototyping, right? And this is basically where the notion of programmable hardware came in, right? It allows you to sort of say, okay, I'll take hardware, but I need to be able to modify it so that it can behave like custom hardware, but without incurring all these non-recurring engineering costs and the long turnaround times, right? And as it happens, this kind of tools that were originally created for rapid prototyping have now become good enough for sustained use in many contexts, not in all contexts, but in quite a few. So like I said, although we call it programmable hardware, technically it's actually reconfigurable. It is, what you are doing is you are literally changing the underlying connections in the hardware that exists, right? It's a generic platform that can be specialized for a particular kind of operation that you want. This has a very long history. These are not new exactly, right? You have programmable array logic, programmable logic arrays, similar but different conceptually. These are from decades ago, probably from the 60s or 70s, right? They have been around. That sort of evolved into this notion of CPLDs, complex programmable logic devices, and eventually to get to the point where we have the modern field programmable gate array, or the FPGA. Now as the name suggests, it's an array of gates that are programmable in the field, okay? And this term field is actually confusing to a lot of people. They sort of think that there is some kind of electric field involved in programming the FPGA. That's not the case. What we mean is that it actually is programmable in the field rather than in the factory. That's why the word field even exists over there, right? So the programmable gate array is the important part as far as we are concerned, and what we will do is talk a little bit about the internals of what a programmable gate array looks like in a moment. So what we want from a FPGA, or in general from programmable hardware, is two things: programmable logic and programmable interconnect, right? What do I mean by that? The programmable logic means that I should be able to effectively make the hardware behave in such a way that it's actually executing pretty much any kind of Boolean function that I want to implement. Now I could write a program that actually does this and run the simulation of the entire thing in a regular processor, right. The point is that's sequential. Every single Boolean equation is going to get evaluated one after the other, whereas if I had a physical set of gates that I could reconfigure or connect in different ways, I actually have the benefits of working like hardware in the sense that the concurrency and the fact that multiple different operations happen at the same time is actually getting used, right. And at the same time I can do this in a way which can be changed later if I find that the functionality that I have got is not really what I wanted. I also have programmable interconnect where I can basically take different kinds of connections, wires from let's say one set of flip-flops and connect them through a set of different switches and wires until it finally goes and connects wherever I wanted it to go, right. So having these two capabilities, programmable logic and programmable interconnect, is the key to having programmable hardware in general, and that is what FPGAs enable. Now modern FPGAs, the most common type are what are called SRAM based FPGAs. They essentially, the SRAM over here stands for static random access memory, which is a particular kind of memory design, right, which is fairly high efficiency, which means that it's quite dense. You can program a lot of bits into a fairly small area, and it is also extensively reprogrammable. What happens over here is this SRAM is actually used in order to hold the configuration bits that decide the contents of various different components of the programmable logic, right. As I mentioned over here, the core concept of a programmable logic is the so-called lookup table, right. And what the lookup table does is it pretty much allows you to take any arbitrary truth table corresponding to either 4 or 6 inputs depending on the type of FPGA and say, okay, I'm not even going to bother about whether this is an AND gate or OR gate or anything else. I'll just take this truth table and put it into that LUT, right. And that configurable LUT can now mimic any other kind of gate that I want. What the SRAM cells over here in this SRAM based FPGA do is they literally hold the contents of the LUTs, which mean, or at least they program the contents of the LUTs in such a way that now each LUT directly has a certain behavior. I can just apply inputs to it, and with a very small picosecond to nanosecond kind of delay, the output is actually present at the output of that LUT, right. So these are the most common types of FPGAs. One issue is that they are volatile, meaning that when I switch off power, they lose the configuration. So you need to sort of work around that and figure out how to make sure that you can bring them back up or reprogram them each time. Another type of FPGA is what are called flash based FPGAs, which address exactly that problem. They are non-volatile, right. But what happens as a result is, how they become non-volatile is they actually use some kind of flash memory in order to hold the configuration. The problem is those flash cells typically have a higher capacitance than the equivalent SRAM cells, and although it may not be obvious right now, higher capacitance in general translates into higher delay, right, and basically makes the chip slower. So you could also have different combinations of these. For example, you could have SRAM based FPGAs, but which as soon as you switch on the system, they basically load their configuration from a separate flash memory, right. So people have figured ways around this, except that now you need 2 chips on the board, so it's always a trade-off. This is how engineering works, right. Alright, so what I'm going to do over here is actually look at a few examples of what the internal structure of an FPGA looks like, and the example that I am going to use over here is from what's called the Spartan 2 FPGA that was released by Xilinx about 20 to 25 years ago, right. Now why would I look at such an old FPGA? Well, because it was simple, right. It's much easier to explain and to understand what's happening inside that FPGA than to really fully appreciate what's happening in a much more modern version of the same kind of thing, and the fundamentals haven't changed, right? The basic behavior, the basic building blocks remain similar, much more powerful and with maybe a few more variations nowadays, but the core ideas are the same. So even though you are not likely to ever see a Spartan 2 FPGA actually in practice, it's worth looking at the data sheets because they are simple to understand, and you can easily get a picture of how CLBs, lookup tables, flip-flops, connection, programmable interconnect and all of those work in the context of an FPGA. And then of course go to the more modern FPGA data sheets and read them to understand how things actually evolved, right. So a common terminology is the so-called configurable logic block, and typically a configurable logic block consists of multiple lookup tables and flip-flops. Okay, so let's look at this figure. Ignore the figure numbers, they are obviously directly snapshots from the data sheet, right? They don't correspond to anything else in this particular presentation. But if you look at it, this looks a little complicated, but we can simplify it. There is one lookup table, there is another lookup table. Okay, let's think about the first lookup table out here. It basically has 4 inputs. Modern FPGAs typically have 6 inputs instead. But the idea is, okay, if I have 4 inputs, how many combinations do I have? 2 to the power of 4, 0, 0, 0, 0, 0, 0, 0, 1 up to 1, 1, 1, 1. For each of those inputs, I can now store 1 bit, right, which basically says, okay, it's either a 0 or a 1, 0 or 1 for all 16 combinations. That's it. So with 16 bits of information, I have managed to configure this lookup table to behave like any Boolean function of up to 4 inputs. The interesting thing is, if I just wanted this to behave like a 1 input NOT gate, I can basically take that input as G1, set G2, G3 and G4 as don't cares, right, or just ignore them, and put in all the entries in the lookup table correspond to, so that whenever G1 is equal to 0, the output should be 1, and whenever G1 is equal to 1, the output should be 0, and I'm done. I no longer have to worry about G2, G3, G4. The output will always be not of G1. Okay. Now that output in turn goes into something called carry and control logic, but the important part is it actually goes into a flip-flop out here, right. So this is, as you can see over here, a D-type flip-flop. It has a reset signal, it has a set signal, it has a clock, it has an enable, right. For the most part, we will be using it as a regular D-type flip-flop. Okay, so this is great. It basically has lookup tables, another lookup table, and 2 D-type flip-flops. Okay, what is this carry and control logic out here in the middle? Well, if you look carefully, you will see that this signal essentially has something called a C in, which comes in here, seems to go through this and through the second block, and finally comes out as C out. In other words, this is literally allowing you to implement ripple carry adders in a very efficient manner. Okay, so that's it. This is just some additional functionality. Why was it put in there? Because of an observation from the people who built FPGAs that addition was one of the most common operations that the users of FPGAs were trying to do. So why not, rather than, you can of course build up half adders and full adders by using these lookup tables, but it's much more efficient to actually use custom logic which is hand tuned or hard coded to do just that. Okay, and this is a common thread that you will see as you go through to more modern FPGAs. What the manufacturers of FPGAs have done is try and identify blocks that are more and more commonly used and then repeat them. Directly make hardware instances out of those blocks so that you don't need to waste time building them out of lookup tables and flip-flops. Okay. An example of that is the so-called memory blocks, right. This is an instance of a so-called dual port block RAM. Dual port meaning that there are 2 ports. You can either write over here or you can write over here, you can read from here or you can read from here. Separate addresses, right, there is an address B and an address A, right, and there is also a write enable A, write enable B, enable A, enable B, and you could potentially even have different clocks and you can run the 2 ports at different speeds. Effectively what it means is you can do something like writing 2 values into a memory block in the same clock cycle, or writing in one location and reading out from another location in the same clock cycle, right. So dual port RAMs are nice to have. More than dual port is very hard to build, which is why they sort of restrict to up to dual port. But this is an example where you can see that potentially you could have built this up out of the flip-flops that are present in the FPGA, but it would be very inefficient because you would need huge multiplexers, you would need the decoders for manipulating the the control signals, the enable signals to the individual array elements. Instead of that, by directly having a memory block like this, it becomes much more efficient, much more compact. Another instance like this is the so-called multiplier IPs, right? There are DSP slices in modern FPGAs which are very good at performing multiplications of numbers. In recent FPGAs, you can have up to one 25-bit number multiplied by another 18-bit number, and all being done at an extremely high speed, right? Because these are like hand-tuned to have really good performance. So modern FPGAs have evolved more and more along those lines, right? What ends up happening is that you actually have more such components that are being designed into sort of hard IPs that are present inside the FPGA. Okay, what else can we have? We want programmable interconnect, remember? How do we manage that? This essentially has the routing block. We have the CLB, right, which has a way of directly connecting to adjacent CLBs, but it also has something called a global routing module, right, which basically says that signals that come from the CLB can go in here and can go across to much farther parts of the chip, which means potentially I could have a wire that goes from here all the way to another corner of the chip without incurring too much delay. I don't need to go through other CLBs in the middle. I have dedicated routing resources that are capable of handling these kind of lines. So putting all of that together, this is typically how the structure of a Spartan 2 FPGA looked like. A more recent FPGA is, to a large part, more of the same, right? It has many more CLBs and more block RAMs and more of these digitally locked loops for clock management, more IO logic so that more pins can be used, right? But apart from that, the structure is essentially the same. Each of these CLBs has some lookup tables and some flip-flops inside it, and this is the array, the programmable gate array that has been constructed out of that. Okay. So as I said, what do modern FPGAs do? And it's well worth looking into the data sheets of modern FPGAs to see how this picture that I showed you over here has evolved over time. There are many more hard IPs. What I mean by that is, a hard IP is an intellectual property core, design that has actually been instantiated directly on the hardware, on the chip, right? Soft IPs are ones where you are given the design in a form like a Verilog code, and then you can go through, synthesize it and put it onto your FPGA wherever it fits. Whereas hard IPs already have taken up some space on the FPGA, but as long as you need that IP functionality, they are extremely efficient implementations of what needs to be done. Right? Examples of that include like very high speed transceivers, transmitters and receivers that allow communication from one FPGA to another, or from FPGAs to, let's say, Ethernet cards or like high speed network interface ports. There are processor cores, in particular ARM based processor cores, that are directly present inside many of the FPGAs, typically the ones from the MPSoC family, right, the multiprocessor system on chip families, that actually have fantastic capabilities. What they allow you to do is to have an ARM processor which is very closely tied to the programmable logic, the FPGA fabric, which means that now the ARM processor can take care of running software including an operating system like Linux, and at the same time the computations could actually be broken down into the programmable logic to run at their own speed and in a more efficient manner in the PL. These are things that will be considered in more detail either later in this course or in the subsequent course on Linux on embedded systems, right? But the important thing to understand at this point is FPGAs are evolving, but the core ideas remain the same. There is programmable logic, there is programmable interconnect, everything else is basically as needed in order to make things run faster or better in some way. Right? Building on top of these, extremely complex systems are possible. In fact, for those of you who are familiar with things like 5G communications, a lot of the base stations and in fact the test bed being developed at IIT Madras, all of those extensively make use of FPGAs for most of their computation, because these are algorithms that are living, that are continuously being upgraded and adapted. Building custom chips to implement these is impractical, because that would mean that you cannot change the algorithms that are running on them, or you need to have a very generic kind of architecture and then write software for it again. The FPGA actually gives you a very nice kind of flexibility in terms of actually reprogramming the hardware when needed. Okay. So FPGAs are a very powerful tool and will be something that we will be using fairly extensively throughout the rest of this course.